we want to develop a graphical and a mathematical model of our data. Now, what we've learned in past, like in math class, if we have a graph with a straight line, I'm just going to label this y and x. We've learned how to turn that into a math equation or a mathematical model. Y is equal to mx plus b. Sometimes people use a k instead of an m, depending on what kind of teacher or which class they were in, but where this m is the slope, and this b here is the y-intercept. So the problem is right now, in this graph that we have over here, we don't have a straight line, right? We've got this curved line. So if you'll see when it says check to see if it's linear, if the answer is no, right, so at this point not linear. So what do we need to do? Well, we need to use graph shape to create a modified graph that is linear, also known as linearize the graph. Okay, so we've got this shape. So now if we check down, I think if I look further in my handout here, which is the graph shape that it looks like? It looks like this one, doesn't it? So perhaps this is not a direct relationship, or not a linear relationship, but perhaps it's a inverse relationship. So we're going to test for that. So how do we do that? Well, instead of graphing y versus x, and I'll remind you in this case it's actually pressure and volume, we're going to graph y versus 1 over x. In other words, we're going to graph pressure versus 1 over volume. So instead of the values of volume here, we want to do 1 divided by the number. If I go back to my data here, now I want to do not pressure versus volume, I want to do pressure over 1 over volume. So here's all my volume data, 0.1, 0.5. Now I could go in manually using my calculator, say 1 divided by 0.1 and make a new data column that way, or I can let Logger Pro do my work for me. I'm going to say new calculated column, and now my new calculated column will be 1 divided by the volume. The short name will be 1 divided by V, and my units will be, well, before they were meters cubed, now they're 1 divided by meters. Again, I can do that cool little superscript 3 to be cubed. And now this is where all the Logger Pro does the work for me. The expression is like a mathematical expression. I'm going to say in that column, I want you to fill it up with 1 divided by, and if I go to variables, all the values from the volume column. So you'll notice that it has quotation marks around it. Now I click done and you'll see a new one showed up. So I have 1 over volume. It's still just graphing pressure versus volume, however. So I'm going to go down here and I'll left click, and it tells me which ones I can choose. Instead of using volume, I'm going to pick 1 over volume. So I do that and I get these values, and they're mostly clustered near the beginning, and there's one here, and there's one way at the end over there. So that looks pretty good. Oh, by the way, if you find that the scale's a bit off, like if there wasn't one there and all the data was from here to here, you can on the graph right click and go auto scale from 0. In this case it won't make any difference, but it's a nice way to auto scale. Now I would like to find, like, I do have a straight line, so I'm pretty happy about this. If I just go back to my notes here, I've linearized it. I've got my notes, so if I go back over here to do my test plot, print your graph. So I'll sketch this one. I'll say okay. Now I've got a nice straight line where this is my pressure, and this is my 1 over the volume, and this is just a gorgeous straight line, right? So let's think about this. Now if I want to make an equation, this is my last bit, if I want to make a mathematical expression out of this, instead of this y equals mx plus b, what will it be now? It'll be, instead of y, it'll be p for pressure is equal to, now something for the slope. I'm just going to put parentheses in there because I'm going to figure out the slope in a second. And now instead of x, it's not even volume, it's 1 over volume. So times, I'll just put a dot for times 1 over volume plus whatever the y-intercept is. So I'll just leave that blank as well. So really what I need to do is look at Logger Pro and figure out what is the slope and what is the y-intercept, and my slope business goes here, and my y-intercept goes over there. So let's see if I can find that. So if I go over to Logger Pro, well, there's nothing written in there. So what I do is I go under Analyze and Linear Fit, because it does look like a straight line now. And boom, now I get this here. See if I can make this a little bit bigger. I'll switch the appearance so that the font's larger. Okay, so here it says linear fit for dataset pressure, that's what they've called it. P is equal to mx plus b, where P is the pressure. Now the slope is 4. And now check out the units. 4 PA/1/meters cubed. Okay, well let's go back and take a look at this. So P is equal to 4. And then the units were, what were they again? Let me just check here. The units were PA/1/meters cubed. PA, let me get in here. PA/1/meters cubed. We'll get back to that in a second. And then the y-intercept, here's the y-intercept, was 0, because it crosses right at that axis. So if I go over here, I'm going to put a 0. Okay, so we're kind of done in a way. Like we have an answer, but I'm a little uncomfortable with it. We should probably make it look a little neater here. So I'm going to say P equals, the slope is 4, has a slope of 4. Now let's deal with those units for a second. PA. Now remember how the units come from. So if we go over here, this is, the pressure is in pascals, and these units were 1/meters cubed. And you'll remember how it works. It's always rise over run is how you figure out slope. So the rise units in this case were the pascals, and the run units were the 1/meters cubed. So you can see how these units come from the way the slope was done, the rise over the run. Now, just a quick little rule about multiply, or for dividing and fractions and things like that. Let's say if I said 3 divided by 1/4, that's the same thing as multiplying. Dividing is the same as multiplying the reciprocal. So the reciprocal of 1/4 is 4/1. So in our quick little example, it's 3 times 4 is equal to 12. So now how would we use that same logic for these units here? So we've got PA, oh that's a little bit thick. We've got the pressure divided by 1/meters cubed. So that's the same thing as pressure times the reciprocal of 1/meters cubed is just meters cubed. So really those units are just, this whole thing here just turns into pressure times meters cubed. So I'm just going to erase some of my mess over here. I'll just erase all this stuff here, and I'm going to say now this is the same as 4 pascals times meters cubed. Now you got to get used to the fact that this number, the slope of 4, has these units. So I want to keep these things together. So just to keep things organized, I'm going to put parentheses around there, because otherwise we might mix up the meaning of meters cubed and the letters that are coming up. So then we get times 1/volume. Now if the y-intercept is 0, we don't need to add it. Okay, now that's looking pretty good for a mathematical model or a mathematical equation. The last thing I could, and this full marks here, I would also say, we could say 4, and here are the units. Instead of saying times 1/volume, I could say, this was our units, so put it like that, over volume, right? So pressure is equal to something over the volume. Now if I go back to that sheet that we had, if I go back to that sheet, so I got to scroll a little bit here. Let's take a look at what this one means, this inverse relationship. Okay, so P over V, as x increases, y decreases. So you can see as x moves to the right, the y gets smaller. Yeah, that looks like what was happening for the data table. We can say in words, we can say it's inversely proportional. Okay, that's what inversely proportional means. So when we graph, we did that and it worked. And so the final mathematical formula is, and again, this was like P equals, this K value is the slope. right? So that was that 4 pascals times meters cubed, right? That's the K value. I could say times 1 over V, so that's what this is saying. Or I could say P is equal to 4 pascals times meters cubed over V, right? So these are the two ways that we put it at the very end. So that you can see how it takes a little bit of work to analyze this, and so that this row becomes something helpful. Well, so that's how you did it. So if I go back, hopefully this makes sense. Oh, we should do the final mathematical equation. Let's finish it up. We'll say P is equal to, if this stuff is in the numerator all by itself, I don't think we need the brackets because it's not mixing anything up, divided by V. Okay, so there would be our mathematical expression. So look what we did. We took this data here. Boom. We turned it into, first of all, and I just want to emphasize this for a second, this is still the main graph for this relationship between pressure and volume. If you look at, that's how you would graph the two. This is a pressure versus 1 over volume, so that you can turn it into a straight line and make a formula, right? So this formula, this mathematical equation, accurately represents this, and it accurately represents that, because this all is the same thing, and it also accurately represents the data. So we would say, hey, in words, it's inversely proportional. If I was to graph it, it would look like that kind of a curve. Here you can see, oh yeah, look, as volume gets larger, pressure is getting smaller, and it works. So that is how you do it. And now you've got some graphing practice to try out. So I think you've got, oh, this is the one we just did for you. So we've done number 1. So you have a few more in your handout to get to, I guess, to get to the number 4. All right, so I'll see you in class.